In this video, I'm going to talk a bit more about allylic systems as we continue discussing conjugated systems. And so in this one in particular, I'll be talking about allylic radicals. So like allylic cations, allylic radicals are stabilized by the resonance delocalization of that single electron. So we can think of radical bromination of allylic systems occurs at the allylic position. So if we have our bromine here, we initiate it with some light so that we get these two radical bromines right here. And so we end up with an allylic system like this. And so we can have this add to any of these allylic hydrogens, which are in green. And so what we can do, we can have this come in down here, that go right there. Those come together so that we end up with our HBr. And so then we have this radical right there, and that can be resonance stabilized. So that goes there, and one goes right there, so that we end up with a radical right there. And so either of those can then be reacted here. So we can have both of these here. We could have this one come in and react with this, or we could have this one come in and react with this. And so we can end up with the bromine on either one of those carbons. And then we can just regenerate our Br2 like this. And so we could continue doing this radical reaction here. And so we want to think about the stability of these allylic radicals. And so we can look at this using the bond dissociation energy. And what we see is that the allylic hydrogen right here, so this hydrogen right here, is actually going to be easier to radicalize even than the tertiary carbon right here. So even than this tertiary hydrogen right there. And it is actually easier to radicalize by 13 kilojoules per mole. So unsymmetric compounds can often give mixtures of products. So we saw up here that we can have this mixture of products. In this one, it just so happened that this was a symmetric compound. But if we have an unsymmetric compound, we can get mixtures of products. And so we can have the allylic shift in a radical reaction. So that would be similar to the 1,4 addition of an electrophilic reagent. And so we have something like this. We start with 1-butene. We can have this radicalize right there at that allylic hydrogen. And so we end up with this radical here. And now we have this resonance where we can have that go there, and the radical end up on that terminal carbon right there. And so we can get the bromine, this bromine radical adding onto either one of those radicals there. And so we can get either the 1,2 product, which is the kinetic product, or the 1,4 product, which is the thermodynamic product right there. So we can end up with it at this second carbon right there, or on this terminal carbon right there. So we can think about the radical allylic system in terms of the molecular orbitals. So the way we usually think about this is as the resonance structure. So we have this radical here. We can have that go down there, that go there, and that go there, so that we end up with this resonance stabilization, which is kind of like having the electron, the single electron, just shared between both of those bonds right there. But with molecular orbitals, we can think about it this way. So we can look at it compared to our cation, or allylic cation, and our allylic anion right here. So with the allylic cation, we end up with just 2 electrons here in the bonding orbital and nothing in the non-bonding orbital. With the radical, we end up with 1 in the non-bonding orbital, and so that would just be our non-bonding electron right there. And then with the anion, we end up with 2 right here in the non-bonding orbital, and so that would just be our 2 electrons there that are not engaged in a bond. So we see here we have this as the bonding orbitals. The non-bonding has this 1 node going through the central carbon there. Then the anti-bonding is right here, where that would give us no bonds going on there. And one thing we also notice with these allylic carbons here is that it actually helps to promote the SN2 reaction. So we can have this without the double bond right here, We can have the nucleophile come in, it'll attack that carbon, then this right here will leave, the leaving group will leave, and we have that going on. But if we have this conjugation here, we can have this hyperconjugation from the double bond between these two carbons here. And so while we are in that transition state where the nucleophile and the leaving group are both still bound to it, we have this hyperconjugation that can actually stabilize that, and that can increase the rate of the reaction. So we can increase the rate of SN2 reactions on the allylic carbon. And so anyway, that was everything I wanted to talk about in this video. In the next video, I'll actually start talking about some of the more interesting reactions we can do with conjugated systems, in particular the Diels-Alder reaction. But anyway, I hope you found this video helpful, and I will see you in the next one.